Hello, and welcome to today's webcast, brought to you by Laser Focus World and Endeavor Business Media. Today's event, investigating 2D materials using new ultrasensitive near-infrared spectroscopy, will be presented by Andrew Zhou, member of the Kim Group at Harvard University, and Sebastian Remy, applications scientist at Teledyne Princeton Instruments. This presentation is both live and interactive, so you can ask questions at any time by clicking the Ask a Question box in the presentation window and clicking the Submit button. We will hold a Q&A session right after the presentation. We do encourage questions, and please ask them anytime during the session is fine. It's always nice to start out with a question or two in the Q&A. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it's recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage at www.laserfocusworld.com. Now it gives me great pleasure to introduce our first speaker, Andrew Zhou.
Hi, thank you for the introduction, John. My name is Andrew Zhou. I'm from the Philip Kim Group at Harvard University. And today I'll be talking to you about investigating 2D materials using new ultrasensitive NIR spectroscopy. So first I want to introduce the 2D materials. So 2D materials came onto the scene maybe in around 2006, 2007 with graphene and other layered materials. And the exciting thing about this material is that it can be exfoliated to the two-dimensional layer and can be stacked into any type of heterostructure. So there have been articles about stacking these, such as like Lego blocks, where you choose the material that you'd like and the heterostructure you'd like to build, and then you just stack them on top of each other like Legos. And the materials come in many different flavors. So there's insulators, semi-metals, superconductors, and semiconductors, and many others that are being discovered and studied currently. And so this opened up a lot of opportunities for people to make new types of combination of materials that before had to be worked through through different growth techniques. Now you can just stack them on top of each other. So today I want to talk to you about. So I want to go over the three biggest 2D materials. So graphene is where it all started. This was graphite reduced down to the single layer of carbon, and it's quite exciting because it doesn't have a gap, and it's a very high mobility 2D material. And then it has its brother, or the white graphene is sometimes what it's called, is a hexagonal boron nitride, which is an insulator. And this material is quite great because it is a large band gap material that can act as a substrate for a lot of these heterostructures that people build. And then finally is the TMD, which is a semiconductor. And when reduced to the monolayer limit, actually has a direct band gap. And so this is the material that we're going to be focusing on today, the TMD class. So what are TMDs? They are transition metal dichalcogenides. They're named because they have a transition metal in the center, and they have two chalcogen layers above and below. That constitutes one layer. And this single layer has a direct band gap at the K points in the momentum space. These K points are locked to both spin and circular polarization. So what this allows us to do is it allows us to use circular polarized light to address individual valleys and therefore individual spin excitons, which are quite exciting. But to go back, what are excitons? Excitons are a bound state that arise from when you have an electron-hole pair. So in this case, we can excite an electron out of the valence band into the conduction band. And if the binding energy is strong enough, then the electron hole pair bound state will form and form an exciton. But since this is a excited state, the electron will recombine, and so this has some characteristic time scale. In the TMD monolayers, this recombination time tends to be about 1 picosecond. And then, so the formation of this exciton, as I said, depends on whether you have a strong enough binding energy. So these materials turn out to have very strong binding energy. So gallium arsenide is a material that we often compare the TMDs to because it is similarly a high quality semiconducting material. But the binding energy in gallium arsenide are only around 10 MeV, which means we're limited to very cryogenic temperatures to do any sort of exciton studies. In our case, for the TMDs, we have around 400 MeV binding energy. So what this means is that we can do these measurements from room temperature down to low temperature, and in general, the energy scale and the temperature that we can explore these materials is at a higher energy. And this is due to this reduced dielectric screening when you reduce it to the two-dimensional limit. So I mentioned before we can stack these materials on top of each other, and so that's one thing. That's what we do with these materials. So the TMDs come in many classes as well. So there's molybdenum and tungsten for the transition metals, and sulfur, selenium, or tellurium for the chalcogen layers. And so if you make these different materials, you can see that their band gaps are varied, and they have different, and if you align them, you can see that certain materials will form either type 1, type 2, or type 3 junctions. And so in our case, we're actually very interested in making a type 2 heterostructure. So we chose MOSE2 and WSE2 as our materials to place on top of each other. So what actually happens when you put them together? Well, first you form a type 2 band alignment, so you can get some sort of PN junction. But also, you can get very interesting excitonic effects when you put the two materials together. One of which are interlayer excitons. So the excitons I mentioned before exist in each individual layer, but in this case, since the conduction band and valence band, when you put these two materials together, exist in two different layers, the electron and hole are actually separated in space. What this means is that the electron and hole are in two different layers. They form a permanent dipole moment, and they're actually, since they're separated, they have it's more difficult for them to recombine. This is actually great for a lot of applications because now that their lifetimes are longer, we can actually manipulate them and do experiments on them. So the first claims of interlayer excitons were in 2015. They show that there is a gate dependence in the energy and luminescence energy, and then the lifetime for the recombination also is much longer, around 1.8 nanoseconds, so 3 orders of magnitude longer than the monolayer limit. So just for a broader perspective, what we actually can do with these is, here's the history that I mentioned before. Around 2005 is when they first isolated the semiconductor, and then they discovered that it's a direct band gap. And then they made all sorts of very cool applications, such as transistors, photodetectors, valleytronics. And now we're trying to do similar kinds of applications with interlayer excitons. But as a physicist, one thing that we're very interested in and trying to explore is what is the actual phase space of these interlayer excitons. The interlayer excitons are two fermions, so they form a boson, so they can condense and do essentially have bosonic behavior. So a theory paper has predicted that below certain temperatures at high enough densities, you can get these kind of Bose-Einstein condensates and other phases of matter that we're trying to explore with these excitons themselves. So now that I've kind of introduced the material and the excitons, I want to go over the overview for the rest of the talk. So first I'll talk about how we actually fabricate these materials, or fabricate the devices, and the experimental setups that we use. And then I have 4 major results. I don't think I'll have time to go through all of them, but I do want to talk about, so we have, since the excitons have long lifetime and they're permanent dipoles, they interact with each other and they can move across our sample. So when you pump with a higher power, you can see the entire sample lights up. You can generate electroluminescence, so driving a current, like a PN junction. We looked at the spatial control, so we make pattern gates and then kind of control how these excitons move. And then finally, we also explored some of the spin behavior of these excitons. But today I'll try to focus on the exciton diffusion and the spatial control of the interlayer excitons in the interest of time. So we'll start with the device fab. So we use a very standard 2D material stacking technique. This involves a glass slide with PDMS and PC. So PC is our sticking layer. What we do is we pair a substrate with silicon oxide. We put our gates and then a BN and contact platinum. And then we pick up a boron nitride layer. So we pick it up by placing the glass slide onto the substrate where the BN is, place it on, and then heat it up and lift it up. And then we can pick up the other layers. So the BN, between the 2D materials, there's a strong van der Waals interaction. So we can use the BN to pick up the MOSE2, then the WSE2, and then we place it onto our substrate that we made. And then we evaporate gates. So these gates are very important because these gates are what actually allow us to control the doping or electric field that the excitons feel. And then CG here is contact gate, which allows us to actually make ohmic contacts to the materials. So this is the resulting sample. On the right is an optical image. So the green areas are the MOSE2, the red areas are the WSE2, and then the blue areas are heterostructure. And so you can see that we have our top gate and bottom gate, and this actually allows us to control the electrostatics of our device. So I didn't mention this, but it is actually quite important to line up the momentum space or the crystallographic edges of our sample. And so we use a technique called second harmonic generation. This is a technique that allows us to align the edges of our materials. And so what we do is we rotate our sample and check our second harmonic generation intensity, and then we can use this to align our sample with 60-degree symmetry. So now I'll move on to the optical setup that we use. So we use a 4F confocal microscope with a Montana cryostat. And so we have 2 lenses that allow us to, with steering mirrors, galvo mirrors, that allow us to put our excitation position at anywhere on our sample, and will be focused to a diffraction limited spot. And since we're exciting, most of our experiments are exciting with 660 nanometers. So we're looking at around 660 nanometers to 1 micron spot size. And we also add in we have a beam splitter and have a second galvo, which allows us to excite and collect from 2 different positions. I'll talk about this a little bit more later, but this is important for the experiments that we do, that I show later in the talk. So I want to show a picture of our experimental setup. Here on the left, we have our Montana cryostat. This is a dry cryostat that allows us to go down to 4 Kelvin temperatures and has been wonderful to use. And then, unfortunately, it's covered, but in the right picture, you can see that there is a box back there that houses our Princeton Teledyne Princeton Instruments spectrometer, which we use for any of our energy for our spectra, which Sebastian will talk about more in the next talk. So I mentioned that we use two different galvos to excite and collect from two different positions. So this is essentially the measurement scheme. We park our laser in a given position by steering one of the mirrors, and then we have a second path that can be collected into either a photodetector or the spectrometer, and then we can scan this second collection all across our sample, which allows us to excite and collect from different positions. We can actually measure how much light is, how much the excitons move across our sample away from the actual excitation position. So this is essentially, unless said otherwise, most of the diffusion measurements are taken this way. So I'd like to go into a little bit of the results now. So I'll talk about our interlayer excitons and how we measure their diffusion. So all of our measurements are photoluminescence. So we excite with 660 nanometers above the excitonic gap of our material. And if you collect from either the WSE2 or MOSE2 regions, monolayer regions, you can see that there are these peaks at 1.7 and 1.6. So these are the exciton trion and some defect peaks for the WSE2, and for the MOSE2, you can see that there's a little bit darker or dimmer MOSE2 with a very bright trion MOSE2. So this is essentially the photoluminescence spectra for the two materials individually, but when you combine the two, we actually find interlayer excitons, which are at much lower energy. So since the two layers form a type 2 band alignment, their effective band gap is much smaller, which is around 1.3 eV, which is where we see our interlayer exciton peak. And you'll also notice that the intra or the higher energy exciton peaks are strongly suppressed. And this is because the electrons and holes are moving into separate layers and preferentially forming this interlayer exciton. So what is the most telling thing, what is the most telling measurement to see if we have an interlayer exciton is that since it's out of plane and it's a permanent dipole moment, it should be tunable with an electric field. So that's exactly the measurement we do. We are collecting photoluminescence, so exciting and with the 660 and collecting the PL energy while applying a electric field. So we apply a voltage on the top and bottom gate, and from this we can generate an electric field. And what we find is that we can tune this energy by almost 200 MeV. So now we have a 200 MeV NIR light source, and from this we can actually extract a dipole moment. So the electric field times the dipole moment is the shift in energy for the first order Stark effect, and this actually agrees quite well with the expected interlayer separation, which is around 0.6 nanometers. So far we are seeing interlayer excitons, and they're widely tunable by electric field. Another measurement we can do is we can check the lifetime of these excitons. And so we do, and we also do this as a function of electric field. And what we see is at 0 gate, we have around 280 nanoseconds, or 260 nanoseconds. This is already 2 orders of magnitude longer than the previous report. But what's actually quite interesting is that the electric field tunes the lifetime. So by stretching and stretching the electron and hole wave functions, you can actually tune the lifetime from anywhere from 100 to 600 nanoseconds. So this gives us some flexibility in terms of the lifetime. It's also quite interesting that the electric field can tune the wave function overlap. So in order to see diffusion, we need permanent dipoles, which we saw with the electric field, and we need the long lifetime, which we observed here. So we now tried to do these diffusion measurements. And so what we did is we excite in one corner of the sample. So if you look at the far left panel, we can excite in one corner of the sample at 10 microwatts, and then collect PL emission, just counts from all across our sample. And we find that most of the excitation, or most of the photoluminescence is coming from the laser position, which is expected. But as we ramp the power up, we can actually see the entire sample light up. So as I said before, this is around 1 micron spot size, but we're seeing photoluminescence from almost a 10 by 20 size sample area. So this led us to believe that we have diffusion, but we had to do some further studies. And so what we did is we did a power dependence, and we radially averaged how much the exciton counts are increasing with R. So if you look at the lower left panel, we essentially averaged over this 90 degree area, and as a function of power, what we can see is that the slope on a semi-log scale changes with power. What this means, what we can do is, if you solve for the diffusion equation for the radial diffusion equation, you can get a dependence of the diffusion length with this slope on the semi-log scale, and from this we can get a diffusion constant. So what we find is that the diffusion constant seems to be changing with power. So normally when you think of a diffusion constant, it should not change with density, but in our case, since we have strongly interacting dipole moments, what we believe we're seeing here is that as we increase the power, we're actually increasing the interaction between the interlayer excitons, which is actually driving the excitons further away from each other. So I hope I have demonstrated that we have exciton diffusion in our samples. And so from here, I want to kind of show that we're actually able to control how these excitons move by patterning the electrostatic gates in our sample. So what we did next is we made a new sample, but now we have 3 different areas, spatial areas, to change the electric field. So we have 2 outer gates, and we have a very narrow wire gate. And so in this wire, by changing only the outer gate electric field, what we can actually do is change the interlayer exciton energy either up or down. So since these excitons are charge neutral, you have to actually change the energy of the excitons rather than changing, for instance, doping or carrier density like you would do in a typical quantum dot. So this is the kind of device that we made. So the area of interest here would be this dashed black line. So the inner diamond would be one of the outer gates. This outer left gate is the left gate, and then in between in this gap, which we can't see optically, is a very, very narrow wire gate that we use in the area which we use to trap or anti-trap our excitons. So essentially, this is the scheme that we're looking at. And so the measurement here that we're going to do is, instead of looking at the counts, well, we will look at the counts, but we can also scan our collection across the outer gate, wire gate, an outer gate again, to see the energetic profile of the interlayer excitons that we're generating. So the first step to controlling and generating these traps, is to generate the correct electrostatic profile. So first thing we do is we check along a line cut across these traps whether we have a uniform energy, which we do. So you can see on this scale that this energy is quite flat when we don't apply any electric field. Now, if we lower the outer gates what you can see is that the outside energies drop down, but the center region, the energy in the center remains at around 1.35 or what it was when it was flat. And you can also see that it's much darker, which is expected when you make some sort of anti-trap type of shape. Now, if you do the opposite, if you raise the outer gates, we actually see the outer energy goes up, but we also see a brightening and still a lower energy in the center wire gate region. So we can demonstrate that we can generate different electrostatic profiles across our sample. And so now we can look at how does the actual exciton cloud shape change. So what does it actually look like when you scan across our entire sample? So the same kind of measurements or same kind of idea, we excite now in the center in this black circle region, and then we collect all across our sample, just the counts that we're seeing. And what you can see is that there's already some inhomogeneous regions on our sample. And when we make an anti-trap, we can drive the excitons away from our excitation spot, but we can't actually drive them away from these brighter spots that are occurring on our sample. However, when you make a trap, what's interesting is that now everything in the trapped region is quite uniform. And now the exciton shape actually resembles the shape of the cloud that we're making. So this is promising because now whatever naturally occurring traps are happening in our sample, we can actually overcome them with a large enough trap depth. So we look at how much of this depth do we actually need in order to generate a trap. And it actually turns out to be quite small. So this is again a flat line cut, but then just by applying a very small voltage, we can see that the trap lights up much brighter, but it doesn't actually get much more bright. It doesn't get much brighter as we make the trap deeper. So from this, it's hard to extract what the actual density of excitons that we're looking at are. So in order to look at the density, what we can do is we can do a power dependence. So by changing the power, we can change the density in our sample, and from this shift in density, we should see a blue shift in the energy. And from this equation, we can essentially correlate our density with our blue shift in the emission energy. And so that's what we attempt to do. We change the power in the center of the trap. So when the energy of the traps are flat, when we do a power dependence, it turns out that we see a energy shift of around 1520 MeV. But now, if you generate a trap and do the same power dependence, you can see that the energy at higher powers is almost limited by the depth of the trap. So the trap evidently is allowing higher number of excitons to stay in the trap region, which makes sense. So from this, we can extract the density. And we find that without any trapping, that we see a shift that's very similar to our previous sample, which is 7 times 10 to the 11 excitons per inverse centimeter squared. But as we increase the trap voltage, we actually can increase the exciton density. And so what are these, to put it in perspective, what do these densities really mean? If we go back to the phase diagram that was predicted, we can actually see that the densities that we're reaching are past the Bose-Einstein condensate. So why are we here? Why aren't we seeing these signatures yet? There's at these high powers, at these high powers and very near the laser spot, the system is not in equilibrium. We could be heating. The excitons themselves may not be at the right temperature, and also this extraction of the density is only valid in the linear regime, but with the strong interactions that we saw in the diffusion, it's possible that this regime is not valid. This equation is not valid for this regime, but it gives us a rough estimate, and it also shows us that we're able to increase the density from where without any trapping. So this is kind of the future direction of what we're looking for, is to kind of explore this phase space by changing the density and or the temperature of our excitons. So as a summary, I showed you the spatial diffusion of interlayer excitons. Then we also were able to control the electrostatic, spatially how the excitons move, and generate a very high density of excitons. So the future is hopefully to move towards kind of these BECs and exploring the phase space, but also these, like I said, we have a very tunable NIR light source, and these can also be used for photo detection or as I mentioned before, we can use electroluminescence to generate light from these heterostructures as well. So before I finish, I just want to acknowledge Philip Kim, who's my advisor, who has allowed us to do all these measurements. Luis Argui, who's now a professor at UC Irvine, has been very instrumental for setting this project up at our lab. Kate and Andres, who worked with us during on some of these experiments. The Hongsun Park and Misha Lukin groups, who were very helpful with the optical measurements, and then theory from Dom and HPN people. If there are any other questions after this session, you can contact me at andrewjoe@g.harvard.edu. Otherwise, I think that concludes my portion of the presentation. So to talk more about the instrumentation and the spectrometer and camera issues that we needed in order to get such high efficiencies at these NIR wavelengths will be I'm sorry. Yeah, will be Sebastian, who will be talking more about these instrumentations from Teledyne.
Awesome. Thank you, Andy, for this great presentation. My name is Sebastian Remy. I'm application scientist with Teledyne Princeton Instruments. And in the really final few minutes of this webcast, I just would like to tell you a few things about some of the new advancements in sensor technology that have been used in Andy's research and greatly increased the efficiency of detection in NIR applications in general. So low light detectors, like we are talking about here, are mainly used in scientific application, but find their use outside of that area when robust, sensitive, quantitative light detection is required. And so desired features of like a perfect low light detector are things like a high quantum efficiency, so that determines how many photons essentially are that are incoming on the detector are converted into photoelectrons and can be measured. Such a detector should have low noise, in particular low dark and readout noise, where dark noise is greatly improved if the camera that is used uses like sophisticated cooling technologies that can cool it to low temperatures. If fast processes are being studied, high frame rates might be desired. And of course, the detector should be highly quantitative, so linear over wide dynamic range. And there are other properties someone might be looking for. So back illuminated CCDs have in this area thus been kind of the workhorse and go-to detectors for sensitive applications. So almost 100% of light can be detected indivisible with such a detector. And typically they have very low dark noise, so they are very quiet. The light-sensitive region in these devices is etched and polished down to a very low thickness, so about 13 micrometers. So that means although the efficiency in the visible is high, the sensitivity in the NIR typically rapidly decreases as the mean free path for absorption of photons increases with the wavelength. So they just pass through the material. The longer mean free path can also lead to interference due to multiple reflections of light on the front and back side of these sensors. And this effect is known as etaloning and leads to these irregular interference patterns in the detected data, as can be seen in an image from such a device on the top right on this slide. However, skillful manufacturers, they can have the ability to enhance the sensors before they are put into a camera to mitigate these effects. So on the bottom right, you see images comparing kind of a standard back illuminated CCD to one of those enhanced devices in the NIR region. And so you can clearly see the effect of this enhancement and how it improves kind of these interference properties. So for achieving even higher detection efficiencies in the NIR, back illuminated deep depleted sensors have been developed. So these sensors use a much thicker silicon depletion region. So instead of 13 microns, about 40 or so. So more light in the NIR can be absorbed. So here on the right, the figure compares the typical efficiency, quantum efficiency of a standard back illuminated and a deep depleted device. And so you can clearly see that the efficiency is increased kind of for higher wavelengths. An additional benefit is that effects of etaloning are much diminished in such devices as well. However, deep depleted devices typically show much higher dark current than their standard back illuminated counterparts, so which can be a problem in applications that might require long exposure times, so minutes or dozens of minutes even. So recently, there are modern sensors introduced that run in inverted mode. That's a mode that can really reduce these restrictions as the dark current is lowered by orders of magnitude. So as such, these deep depleted sensors provide, up to now at least, the state of the art in terms of detection efficiency in the NIR. So the most recent development in this area are what we call super deep depleted or HR sensors. So these are devices that are manufactured from a high resistivity bulk silicon, and they are almost 4 times thicker now than even the back illuminated devices. And so as such, they can absorb even more NIR photons. And so in addition to being thicker, you apply even an additional bias voltage to assure a full depletion of the light-sensitive area and to increase the spatial resolution of these devices so that they perform just as their counterpart in this regard. So once you go into NIR, practically, this means depending on the wavelength, you can now get 2 to 7 times higher efficiencies than with the current state of the art. So in particular, when you observe close to the detection of limit of silicon, so let's say between 950 or 1100 nanometers, something like that. So in this wavelength region, the sensitivity of current state of the art device is already kind of falling down. And so if you want to measure with high quantum efficiency at even longer wavelength, one possibility is to use yet another kind of devices made of in-gas material. However, those devices are typically much more noisy as well. So currently there has always been a small wavelength region, as you can see kind of in this graph, where the efficiency of silicon kind of falls down, while you don't have yet high efficiency with in-gas devices. So there's a small region that is not really well covered with high efficiency detectors. So these new HR sensors really well cover this drop in sensitivity to assure kind of continuity in high detection efficiency. And in particular, going up to around 1100 nanometers, they are typically probably even much more efficient and sensitive than in-gas devices, even when the QE is lower because of their much lower noise. So to illustrate that, I just wanted to quickly show this graph, which represents a measurement of an atomic emission lamp in this wavelength range. So this measurement has been taken with an in-gas camera. That's kind of the orange line you see kind of in the background, as well as with these new HR sensors, which is the blue line. So you clearly see that the sensitivity is significantly larger for HR. So in particular, I like to look at like many of the lines that are really clearly visible on the HR sensor that almost disappear in the noise for the in-gas device. So these devices can provide great benefits for practical measurements. And so in the final few slides, I want to quickly show you a few applications that really profit from these new, more sensitive sensors. So the first application example I chose is bio-Raman spectroscopy. So in bio-Raman, you typically excite with wavelengths of 785 nanometers or even higher wavelengths. So the Raman signal you measure stretches deep into the NIR. And so the reason to use these high excitation wavelengths is typically to avoid autofluorescence that happens in tissue, and that really overwhelms the really weak Raman signal for lower excitation energies. So using NHR sensors, the signal at even higher wave numbers can be detected with higher sensitivity. So on the bottom right is kind of an exemplary measurement of cyclohexane going out to 3,500 wave numbers. And on the top right, you see a graph comparing Raman spectra taken on actual tissue samples with an HR device shown in red compared to the current state of the art device shown in blue. And so one can clearly see the sensitivity advantage of the HR device, and that brings really tangible advantages actually, like a reduction of data acquisition times, so one can get like high confidence results faster. That can be important to obtain like faster diagnostics in medical applications, for example, like cancer detection or things like that. Also, great information can typically be gained from making scans, so creating images of samples, typically using confocal Raman scanning techniques. And so having a higher sensitive device allows to reduce the acquisition times because the acquisition speeds can be increased. So just really briefly, you heard a lot about Andy's research during this webcast already. So here I just wanted to show a graph from some tests we did on Andy's devices comparing the HR sensors to the current state of the art that showed, depending on the wavelengths, up to something like 5 times increases in sensitivity of the PL emission detection. So here in orange, you see the HR device. In purple is the current state of the art device. So what I wanted to point out furthermore is the thicker HR sensor even further mitigates the effects of etaloning that I mentioned earlier. So if you look really closely, you see on the purple line some oscillations that are actually due to etaloning that are missing on the HR device. So that gives you even higher confidence in the data you collect with these types of sensors. The very last application I wanted to present is based on research by Professor Hideaki Kano in Japan. So this group is doing coherent anti-Stokes Raman spectroscopy, and they combine this with scanning samples point by point to collect Raman images. And so they also use supercontinuum light sources, and that achieves really an ultra multiplex CAR system, they call it, where they basically probe a wide range of Raman wavelengths with this technique simultaneously. And so using HR devices, they could achieve unprecedented speeds with dwell times in the millisecond range. And so where the improvement in speed was, according to the researchers, mainly due to this higher sensor efficiency. So that's really important for them to establish these CARS techniques and measurements as a fast diagnostic tools in like biophysics, engineering applications. So that's really interesting research being done there. So finally, I hope you had a good time during this webcast. We are always happy to discuss your application with you and see if we could be of any help in your research or instrumentation needs. You can find us at princetoninstruments.com. And with that, me or Andy and me, we are looking forward to your questions. And yeah, thank you so much.
Thank you, Andrew and Sebastian. We're now in the Q&A portion of the webcast. So once again, to ask a question, you click in the Ask a Question box in the presentation window. So I will just pose the question, and whoever wants to can jump in to answer it. First question, why choose MOSE2 and WSE2 for the heterostructure?
Hi, so yeah, I can talk about that. So the two materials actually are ideal in terms of the optical setup that we had. So the MOSE2 and WSE2 are right in the visible range, and the resulting interlayer exciton is tunable right up to the edge of this Blaze camera's quantum efficiency. And so this actually allows us to, this is ideal for the optical setup that we have, and also has the highest quality optical individual monolayer crystals as well.
All right. Next question. Can the diffusion be explained by any other means, such as temperature or laser shape?
Right. So this is actually something we had to study quite carefully. And if you check the archive paper, we go into much more detail about how we really prove that we have diffusion. I think one of the most telling measurements we did was we keep the power of the excitation fixed, and then we change the electric field. So the electric field changes the lifetime of our interlayer excitons, and then what we can see is this diffusion length will change based on the lifetime or how long the excitons have to move away. So this is we talk about it in more detail, but essentially this takes away any of these temperature or laser shape possibilities that would essentially, as we increase power, would change the essentially the landscape of our excitonic heterostructure.
Okay, and we have one more question here. Regarding the experimental setup, what were the deciding factors for choosing the spectrometer and CCD camera?
I guess, yeah, I can talk a little bit about this, but we worked quite closely with Sebastian on this. So we were able to demo this Blaze camera that Sebastian has been talking about. So in one of his last slides, we actually show this comparison of essentially the Blaze camera from the camera that we had before, and I think we tuned our excitation energy to as far into the NIR as possible. The fact that we were able to see this 5-fold increase was pretty much what sold us on this experimental, essentially on the camera itself.
Mm-hmm. Yeah, I just want to add that I find it also quite remarkable for these devices that achieve almost 100% efficiency. So getting kind of a progress where you have such kind of a big leap where you get like a multiple kind of in detection efficiency is, I think, really rare. So that's quite exciting about kind of these new devices. So.
All right. There aren't any more questions. So would either or both of you like to make any closing remarks?
Andy, you want to go first?
Yeah, I can talk about it. So, yeah, I think the 2D materials are a very exciting field right now. It especially with these now with the increased efficiencies in the NIR regime, there are a lot of materials such as MOT2, smaller bandgap materials that we couldn't measure before. And I think it's really accessible to a lot of people. These monolayers can be exfoliated using Scotch tape. So anyone that wants to do optical measurements on these materials can really get into the field. And I think, I think that's one of the exciting reasons that we're in 2D materials.
Yeah. And then from my point of view, so that's really exciting research. I think I just scratched the surface probably on applications kind of there. So really everything that utilizes detection and NIR and is of low light kind of nature would profit kind of from this type of instrumentation. But yeah, so that's kind of it from me. So thanks everyone for listening in.
Okay, well, on behalf of Laser Focus World and Endeavor Business Media, I'd like to thank today's speakers, Andrew Zhou of Harvard University and Sebastian Ramey of Teledyne Princeton Instruments for today's presentation, Investigating 2D Materials Using New Ultrasensitive Near-Infrared Spectroscopy. The presentation will be archived within 24 hours and can be reached from our homepage at www.laserfocusworld.com. A reminder email message will be sent to all registrants, complete with a direct link to the archive. We thank you for joining us today and look forward to serving you with future webcasts.